So today I would like to broach a new subject. It is also the most central issue involved if you take a theoretical approach. It's the subject of transformations of the Euclidean geometry. I shall not make a systematic approach to transformations of Euclidean geometry. I will not, as I say, make a systematic approach. I will merely go through a list of the more important transformations that are characteristic of the Euclidean geometry, and I will show you the way such transformations can be used in solving problems. It is, in fact, one of the magic aspects of geometry that geometric transformations can turn a problem into something which is. So that's going to be essentially my approach. Okay, so without really going into the in-depth into the subject of how a geometry is defined by either transformation, etc. No, I'm not going to do that kind of thing. Okay, so as I say, it's essentially a glorified list. So I will first talk about some isometries. Okay, so in fact I will do it in two parts. I will talk about isometries. So these are, so to speak, the rigid motions which leave distances, angles, etc. Everything's fixed. And B, I shall talk about homotopes, which differ very little from isometries, but they can change the length, although they leave the angles fixed. Okay. So of the isometries, so the isometry, so let's take part H. So as I promised, I shall be going through a list. And the first of isometry that I shall take up is okay, so that's A. Transformations. Translations. Okay, so let's make it like this. One, translations. Well, I do not wish to go into a verbal definition. I will avail myself of the analytic geometric notation. Translation. So a translation will be, well, I shall denote it by capital T, and a translation will be given by a single data. It's a vector U. Okay, so this thing, so let's identify as usual the Euclidean plane with R2, and as I said, as I promised, I'm using the language of translation along a vector U, or translation by a vector U, is the map that takes every point X into the point X plus U. The picture that you shall have in your mind is simple. So for every, so you've got this vector U. Okay. So of course you are quite familiar with vectors, but imagine it as a arrow, as a quantity which has got also direction. Anyhow, so what you do is, for every vector and for every point, you just take the vector and push the point X find a vector u. Okay, so something like this. So if you've got, let's say, another point like this, then now, I mean, even very simple, very elementary drawing, some parallelogram has a special position whenever you are interested in translations. That's true. Okay, so that's and in fact, you can make it a thumb rule. You can make it a thumb rule that if you have got a problem in which there are numerous parallelograms, it might be simplified. It might be simplified if you use translations. Okay, so I would like to. Okay, so that's the definition, which is rather boring. Some examples of the uses to which translations can be put, and yeah, well, here is one thing that is let's say okay, so application. Let's call this application. Now that is actually a rather simple elementary problem, and of course, you don't have to solve. I shall solve it, or let's say I shall transform the problem into a easily manageable problem, into a much simpler problem, in my opinion. But of course, you don't have to do the same thing. You can use other methods. You can look at the problem in quite a different way. But here's the thing. A classical problem, an elementary problem. An elementary problem. It goes like this. So given a parallelogram, you are given a parallelogram. Given a parallelogram. Well, my observation is immediately revindicated. Parallelogram. Parallelogram. Okay, so ABCD, let's say. ABCD. And a point. T. Such that the angle TAD, I shall now draw a picture, is equal to the angle DCT. Okay? So given this data, you are asked to prove that, namish, okay, the angle ATD is equal to the angle BTC. Okay, so how is this to be done? Well, so I mean, as I say, you can do it in many different ways. So let me do it like this. But you don't have to follow my solution. But I think you will also agree with me that this problem can be considerably simplified by looking at it through the glass, so to speak, of transformations. Okay, here's my parallelogram. Does it look like a parallelogram? Yes. A, B, C, D. And you've got some point. Now that's the difficult part of the drawing. A, B. Okay, so it is T, A, D. Just yeah. Okay. So here is a point. Okay. Now, yeah. Here's a point T. Okay, and here is the characterizing property of the point, that the angle TAD, well this, okay,
and the angle DCT, so they're all in the negative direction. So these two angles are equal. Okay? So that's how you start. And the problem asks you to actually to show that this angle, so the angle which I'm marking 1, is the same as this angle. Right? So you are given that the angle here, that's the angle TAD, I'm sorry. TAD is equal to, okay, TAD is equal to DCT, so these two angles are equal. You are supposed to prove that the angles marked 1 and 2 are equal. That is, of course, a very elementary problem, and you can approach it any way you like. But the translations help as follows. You see, I mean, even in this picture, the effect of translation and the natural way in which parallelograms crop up. Okay, so that's your vector. Okay, and the point is moved into this, and this point is moved into this, and observe that you've got all parallelograms. So, I mean, the very first picture that I drew on the blackboard makes it clear that translations has got something nice to do with the parallelograms. Okay, so I would like to. Well, this is a little bit pulling something out of my sleeve. Yet, okay, so if you can forgive that much conjurership, okay. Let's move everything down. Okay, let's move the point T, not everything, along the vector AB. So the vector T, the point T moves along the vector AB like this and ends up in here. Point T prime, let's say. So T prime, I'm telling you, is obtained by. Did I call the translation T sub U? Let me make it TR. That is more telling. That's more telling. Okay, so this point T prime is obtained from T by moving everything by vector AB. Good. So what happens? So what happens is a simple observation you've got there. You've got there a simple observation. Of course, if you, okay, so I don't know, perhaps I should, okay, so perhaps I should mark my original parallelogram. So in bold yellow, okay. And of course, what happens from T is also part of the interesting problem. So the rest is my invention, so to speak. Okay, so if I join T prime C, you notice first of all that this angle, let me mark it by 2, is of course 1 is equal, 1 is equal to, okay, so let me call this 3 if you like. 1 is equal to 3. That is, that's quite simple. Besides, of course, this angle here, the angle CBT prime, is of course the same as this. So what does this tell me? Since this angle and this angle are equal, so is this angle, okay? Well, that tells me, of course, that the angle CBT prime and the angle CTT prime are equal, so these two are equal. So it means that, okay, let me show you quite explicitly. It simply means that the points T prime, C, and B, they are concyclic. They lie on a circle. Okay, so let me note that. Let me note that. You notice that the points T prime CB, T prime CB are concyclic. So they lie on the same circle. Concyclic. Well, since, okay, so you can imagine that there is some kind of circle, okay, going through them all. Well, if that happens, then you're done, you're finished, because you see, in that case, let me see. Okay, in that case, yeah, you're finished, because you see, the angles which I have marked 3 and 2 are exactly the angles which are subtended by the arc CB in the points T prime and T, so they are equal. So that means, okay, so since these points are concyclic, I've got 2 is the same as 3, and of course I know that 1 is the same as 3, so there we are, finished. So these two angles are equal. I mean, it's all a matter of taste. It's all a matter of taste. Now that you have seen it, you will find it simple. You might think that the way I approach it, the method that I have introduced, is just too convoluted. Translate things and find concyclic things. But try to approach this problem directly and in an elementary fashion. You will find that you won't make much headway. It's the kind of problem in which appearances really deceive. You will be hard put to find an elementary solution. Okay, so that's one example in which you can use translation. Right. My second application, and with that application, I think I shall run out of time. Yes. With that application, I shall run out of time, of course. I think, perhaps not. That is the second example is again a classical theme. So let's say this is application 2. You can put it into you can make a drama out of it, okay? And I shall, to a certain extent, it's in fact a simple problem of geometry. I mean, the problem is simple, the solution is not quite apparent. Okay, here is the thing. So you've got, okay, so let's assume that, okay, so this is the bridge. Across river. The bridge across river problem. This is, if you wish, one of your minimum maximum problems, which are familiar, which should be familiar to you from calculus lectures. However, yeah, we shall solve a maximum problem without actually taking derivatives or something. That will be not. Of course, by the way, you can solve this problem by using calculus too, but let's see if we can do that. Here's the thing. There is a river. Okay, so I shall represent it as two parallel lines. River, which has got a definite okay, so the distance between two sides of the river is I assume a fixed quantity. I mean, it's not changing, and I'm assuming, to make things simple, that the river is following a straight line, and on two sides of the river, there are cities. Let's say one is in here. There is one city, and there is another city, so I have to go right like this. As the city A and the city B, like this. Okay, I don't know, whatever, village, however you might like to understand it. The question is, so you want to build a bridge on the river. So the question is where to put the bridge so as to make the distance, the total distance from A to one coastline of the river across the bridge and the walk to the next village. Okay, how to make this distance as small as possible? Well, let's look at it this way. So if you, for instance, put the, so for instance, people in the town A may think greedily and say, let's make the bridge close to us like this. Okay? So let's say this is the XY situation, okay? And of course, in that case, what you will get is this. You will walk from A to one bridgehead at X, and then you cross the bridge, and then you walk from the other bridgehead to the next village. So that's going to be that's the total distance that you have to traverse going from A to B across the river. Good. So the question is, of course, find find the position. Of course, by the way, you are making, of course, all sorts of assumptions which appear rather natural. So the bridge will be built so as to be perpendicular to both coasts of the river. Otherwise the bridge will be too long. Let's say the cost of the bridge is so high that we can't afford that. Anyhow, so the bridge is in this shape. Find the position of the bridge. So where should the bridge be built? Bridge XY. The bridge XY, which makes the distance, okay, so AX plus XY plus YB minimum. So as small as possible. As I say, you can approach this problem in many different. You can actually have a go at it using calculus, and you will get the same results. The idea is, however, using geometry. The idea is you imagine. You see, the thing is complicated only because of complicated by the presence of the river, actually. So if there were no river, if you have got the towns A and B like this, if you want to go from town A to B, all you have to do is just to follow the straight line that joins the town A to the B. That would be all. But the river complicates the situation. So the idea of the geometric transformation is to make this difficulty disappear. To make it disappear, you take the vector, let's say U, okay, which moves, of course, in our mind, one coast of the river into the other coast. So it's, in fact, this U is, so to speak, the width of the river. Okay, how long? What's the distance between the two sides? Okay, so what you do is you move the city in your imagination, of course, you move the city along the vector U, so you get to a point B prime, which is, of course, the translation by U of the town B. Okay, so you have done this. Okay, so you have obtained the point B prime. Now the curiosity is that the distance that you give from A to X, X to Y, Y to B can be understood as follows. You can take the distance moving from A to X and then from X to B prime directly. You see, if you do that, B, Y, X, B prime, this is a parallelogram. This is a parallelogram. So actually, the two sides are exactly the same. The two sides are exactly the same. So let me draw the parallelogram for you. Okay. Okay, so actually, now looking at this, instead of trying to understand the distance that you have to traverse, traveling from A to X, X to Y, Y to B, we can instead forget actually the width of the river, and we can just concentrate on the shortest distance between A and B prime. Well, that is very easy to do, because you see, all you have to do is just to take a straight line that joins A and B prime. Victor, I'm sorry, this has turned out to be too close, but that is exactly where you have to put your bridge. You have to put your bridge, okay? Because you see, if you do that, this is what's going to happen, okay? You see, look in. Okay, so let me call this thing X hat, and let me call this Y hat. Now, if you choose your bridge hat to be X hat, then you see the distance that you travel from A to X hat to Y hat to B is exactly the same as, let's leave X hat, Y hat fixed because it's the same as XY. It's in fact X hat, B prime, which is a straight line, which is a line segment, which is the line segment joining A and B. It's of course less than AX, XB prime, which is XB prime can be replaced by YB. Okay, so I write the following. So in fact, the distance AX hat, that's and plus X hat, Y hat, and Y hat B. Now this, okay, so this is not interesting because this is in fact exactly the same as XY. So we can forget it. Okay? So this is in fact, okay, so this AX, look, AX hat plus Y hat B, I can replace this. Okay, so I can replace AX hat. Let's leave AX hat as it is. Y hat B, I can replace with X hat B prime. And of course, this is the same as XY, so let me replace it with XY. Good. So this object, however, is just the line segment joining AB prime. But this line segment AB prime is of course definitely less than the broken line AX and XB prime. So AX plus XB prime, and that's, I've got XY, and of course this XB prime is exactly the same as YB. So I've got the following: AX plus XY plus YB. That's it. And that happens, of course, for every X. So this shows you, this is how you construct, this is where you construct your bridge. And in fact, this is really I don't know, it's a rather amusing problem of civil engineering, if you wish. So let's repeat. What you do is you move the town B in your imagination, of course, to a point B prime by the translation that moves one side of the river to the other side, okay? And not having found B prime, all you have to do is join B prime and A and let it intersect the one coastline, the upper coastline of the river in the point X hat. Your solution is X hat. And that shows you quite clearly that once you put your bridge here, so if your bridge is in this part of the world, the bridge is in this part of the world, then the way which you have to traverse, traveling from A across that bridge to B, is shorter than all other possibilities, which is a remarkable thing to happen. And that, by the way, okay, I ask you, try the same problem. Try to obtain the same result. By calculus. You will, it can be done. Actually, when I was very young, someone asked this problem, and this kind of solution is not easy. I did it by calculus. It can be done. The difficulty in calculus is, you will find where the point X hat is, but it is important to be able to analyze where that point lies, and so it's not easy to find that. It's actually the point in which the one side of the river and the line AB prime intersects, where B prime is the point obtained from B by translation along the vector AB. And that's not easy. It can be done though. So that's calculus. Now let me see. So I've got quite a number of axes, quite a number of interesting applications of translation, and let me see if I can find it. Oh yeah, okay. So let me find. Okay, so no, that's quite sufficient for translations. So. Right. Okay, so I would like to present you. So I've got about 15 minutes time, so I can give you a very short, brief talk. And I would like to introduce yet another transformation. So the first one was translations, and I would like to talk a little bit about reflections, and I don't need to explain that, reflections. And well, as you can see, each transformation is given by a certain amount of data, and the data in the translation consisted of a single object that was a vector. For the reflection, again, we need a single piece of data, and in fact it is, so I shall write it like this, reflection, K. Now K is any. Okay, so let me, the reflection in the line K. So the English language has got this peculiarity. I mean, looking at it as Turks, the Turkish language always says reflection from something. Okay, so aynadan yansıma, sudan yansıma, okay? So duvardan yansıma, okay? So that's always reflection from something, or reflection on something, perhaps, occasionally. It's rare, more rare. But the English language talks about reflection in a mirror. Reflection in a mirror. Reflection. So we shall be talking about reflection in the line K, so small k. So given a line K, I talked about, okay, so that will be denoted by a reflection K, ref sub K, that's the notation that I shall adopt. So what happens is, okay, so it's something well known to you. So you've got this straight line K, and to find the reflection of any point x in the plane, and let me take x for the moment, not on K. All you have to do is to find the point, okay, so drop a perpendicular from x onto K, and then produce it until you find a point x prime, which has the property that the straight line K is the perpendicular bisector of x prime. So this sends x into x prime in such a way that K is the perpendicular bisector of the line segment x prime. Now this is provided x is not on K. Okay, so let me draw yet another picture. For instance, you've got, let's say, y, again not on the straight line K. So what you do is you drop a perpendicular and you produce that perpendicular until you reach a point which has the property that the straight line K is actually the perpendicular bisector of the line segment y prime. Now, if, however, you take a point on the straight line, then the reflection, you know, we have got this wonderful and so often revisited, so frequently recurring theme in old literature, divan edebiyatı, you know, in older Turkish literature, I think in Persian literature too. One talks all the time about the mirror and the dusts on the mirror. And for some reason, that's very important. It's got great allegorical value. So the dust on the mirror, this very tiny microscopic granule on the mirror, it's its own reflection. Okay, so that is reflected into itself, right? Okay, so that's what happens if you've got reflections. Okay, so about the reflections, there is yet another point that is important. I mean, it's quite obvious, isn't it, that if a reflection in a line K, if you take a reflection in a line K, if x is sent into x prime, obviously the very same reflection will send x prime into x. Okay, so a reflection is, that's what the algebraic expression for it is, that reflections, so a reflection is what the algebra people like to call is an involutive map. As an involutive map, so that means if you take a reflection in a line K, and if you repeat it, so what happens is a point x is moved into, let's say, x prime by a reflection, and that point x prime, if you apply the same transformation, is transformed back into where it has come from. So the total effect of, net effect of taking a reflection and applying it twice is just the identity map. So nothing happens, everything sits where it has started. So check that word. So this involutive means that if you take a map phi, and if you take its square, it's the identity. Okay, so that's involutive map. This is an expression which the algebra people just love to use. So let me finish. I would like to finish by giving a very simple, very simple example. So, okay, once again, let me express it in a dramatic form. Okay, so let's say application. Let's assume that we've got once again a river or application. So let's say I don't know. You've got something like a lake or something, whatever. So there is water in here, lake, let's say. And let me assume that the coastline is a straight line, and there is a town A, and there is yet another town B, okay, like this. And okay, so let's say that this is a very harsh climate, something like desert, okay, there is no water on the land. So everybody going from town to A to B, they do not dare to undertake this voyage on a straight line. They first visit the lake, so everybody must somehow walk to the lake, and then, okay, let's say, okay, they drink water, or they, I don't know, they fill their reservoirs or whatever, tanks, and then they start walking towards town B, towards the town B. Of course, this is rather stupid. I mean, of course, they would of course follow straight lines like this. Okay, so you go to a point X, and then on the coastline, and then you go to the city B. Okay, so the question. Okay, so let me as usual put it into a little bit more dramatic language. Okay, so the question is, çocuklar, so here's your coast. Here's the coast of the lake. So you must go to the point X. Okay, so the question is which X? So which X on the coastline you must visit so that the total distance that you traverse traveling from A to B has the smallest possible value. Now let's have a look at that. Okay, so the idea is is to take a reflection of this B. So you construct an imaginary town across here, okay? And now you notice the following. The distance AX plus XB is exactly the same as the distance, okay, so these two are equal, AX plus XB prime. So that means actually what you are doing is, I mean, you can imagine that instead of going to the town from town A to B, you can imagine that you're actually going from the town A to B prime, okay? And stupidly enough, if you use this X, then it's a broken line. To make it the shortest possible way between 2 points is, of course, the unbroken line segment. So what you do is just you just take the path from A to B prime, a straight line, and that is your solution. That's your x hat. And if you go to x hat, then okay, so this is the shortest possible distance. So let me show you, because you see, if you take this road, then okay, so let's see. So if you go from A x hat plus x hat B, well, you see, x hat B is in fact the same as x hat b prime. But you see, this sum is simply the length AB prime, so this is always less than the sum AX, so that's the broken line, plus XB prime. But you see, this is exactly the same as AX plus XB, right? So if you choose the point at which you shall arrive the lake, you shall arrive the lakeside in this manner. How? By creating an imaginary town, by reflecting the point B, the town B in the coastline. You obtain the imaginary town B prime, and you join A and B prime, and you let it intersect the coastline in the optimal point. This is rather remarkable. In fact, şuna bakın, if you look at it, this angle, let me call it 1, is of course the same as 2, and this angle is equal to 3. So this is in fact the orbit that a light ray would follow if it were going from A to B, and if it were being reflected in a mirror. Now, that is something rather remarkable. So assume that this is a mirror. This is a mirror. Let's assume that this is some light source. Here is the mirror, okay? And I'm looking into the mirror and I'm seeing something in the mirror. Let's say this is the star Sirius. Some very distant light source. And here is my eye. That's me. I'm looking at it. And in the mirror, I see the star Sirius. That means it means that actually a photon, in fact millions of photons, but a photon leaving the star Sirius is following exactly the orbit to the mirror and to my eye, which makes the distance traversed a minimum. Now that's a great curiosity. Why? How should a photon know that? Why should it work like this? In fact, in 17th century, when people discovered principles like that, people thought that this had a great metaphysical meaning. Okay? There were a quite number of serious-minded people who thought that this was final, irrefutable evidence of creative intelligence, okay, existence of God. Okay, so the universe is working in such an intelligence fashion. There is in fact intelligence built into it. This is the only way to express it. Okay, well that's exciting. Well, I don't know. I'm not that kind of person. I can't see that. Anyhow, but this was a very exciting idea. Okay, so let me conclude. It turned out that the next century people discovered, in fact, that, well, as far as we know, all differential equations governing physical phenomena can be seen as minimal. Something is minimized. Take any problem, electrostatic, hydrostatics. Take the mechanical problem of the pendulum. Any kind of problem, any complicated problem, any simple problem. It is always the solution of a problem like this, and there is some quantity which is being minimized. So that was the great discovery of the modern physics. Okay, so this is really the beginning of a beautiful story. Okay.